we are continuing with module 4 design of general purpose industrial helicate gear reduction unit part 2, and this is lecture number 18, where I shall cover bearing selection and introduction to Saps design verification. Now, already we have calculated the loads on Saps. So, now we shall go for bearing selections for intermediate Saps, choice of bearing from catalog, choice of factors for estimating equivalent reaction loads on bearing, estimation of equivalent reaction loads on bearing, estimation of lives of bearings, search for more appropriate bearings, and then final selection of bearings. Next, we will go into introduction to design verification of shaft. Calculation of bending moments on shaft also will be introduced. Now, we have chosen the intermediate shaft for selection of bearing and design. Reason is that if the intermediate shafts size bearings are finalized at first, then it will be easy to select the bearings for other two shafts, that is input and output shafts in this case, because this is a 2 stage. In case of 3 stage, obviously there will be 2 intermediate shafts. In case of 2 stage gearbox, only 1 intermediate shafts. Now, we have already calculated the loads on this shaft along with the bearing reactions. We have resolved the gear loads, that is normal loads on the gears while it is transmitting torque, into basically 3 components in case of helical gear. One is that radial load, and then again this radial load we have resolved into the 2 parts, horizontal and vertical plane, and then axial loads, which is acting along the axis of the shafts. In this case, after that we have considered the bearings. While we have calculated the load, we have estimated that bearing width will be within 25 millimeter, and from that we have found out the load point of the bearings. Now, after selection also we will arrange the bearing in such a way that will remain same. So, whatever load has been calculated, bearing reaction has been calculated, that we can accept for the next part. In this case, what we find that this is the vertical load, at left hand bearing, and this is the horizontal load at left hand bearing, right hand bearing, which are given here, and also the in horizontal plane at left bearing it is 520 Newton, and in in left bearing it is 720.6 Newton, and right bearing it is 520 Newton. Whereas, these are the acting load the tangential load at this tooth, we should remember that this is the plan view, top plan view of the gearbox. So, this means that torque is entering from here and going like this, going in these directions, and direction of rotation we have taken like this. So, at this point the tangential load is acting upward, and at that point tangential load on this teeth is also acting upward, which is shown here. Now, the radial loads is acting from this side. So, on this gear it is F R2, and on this pinion it is acting from the other side, which is F R3. Then finally, we have calculated the axial loads. Intentionally the helix angle have been taken in the same directions for both gears. This is left hand. So, for the gear first stage gear. So, for the pinion of second stage also has been taken left hand, so that this axial force acts in opposite directions. Say if this is the directions and load is coming upwards, then axial load must be in these directions. Here if this is the directions and load is coming from this side, so axial load will be in these directions and they will oppose each other. And from there this also we have noted down here, the what are the radial loads in these directions. So, final directions will be in this direction as it is higher, this value is higher. So, these are the resultant load, because we have resolved the load in vertical and horizontal plane, and then again while we are considering the bearing calculations, then we need to consider the resultant of this load as a resial load. And interestingly, these load are not in same plane, although it is shown here in the same plane, but if we observe, this is the angle 13.25 degree, whereas this is 11.57 degree. And in first attempt, without resolving the forces in horizontal and vertical directions, it could be difficult to find out these two reactions load. Now, resultant axial load may act only on one bearing irrespective of its direction of shaft rotations. Look at this, if we rotate the shaft in opposite directions for the same load, say suppose it is rotating in these directions. In that case, the tangential load will be from the top, here also it will be from the top, because it is rotating like this, and then the axial force will act in other directions on these two gears. But resultant force, they definitely will be opposite in this case if we rotate the direction of rotations. Now, depending on axial load on bearing, depending on the bearing locking arrangement, axial load may be taken by only one bearing. So, in this case, we have locked this bearing by circlips. There are one external circlip on the shafts, and the same side there is another internal circlip also, and other side inside the gearbox sides there is another circlip. So, this is one circlip, this is another circlip on the housings, and this is the circlip on the shaft, and this is the step where the bearing is held. That means bearing positionally locked with the shaft as well as with the housing, and other side it has been kept free. So, therefore, whatever may be the direction of rotations, the axial load will be taken by this one. For clockwise rotation looking from right hand side, the resultant force will act in this directions, and then the bearing will be pushed by the shafts, whereas in case of rotation in anticlockwise direction looking from the right hand side, this resultant axial load act will in this directions. This means that this load will be transmitted to the bearing by pulling the bearing in this direction, as the outer race is fixed and also the inner race is fixed on the shaft. So, thrust load will act accordingly on this shaft. So, this is important, that how we will lock the bearing and which bearing will subjected to take the axial load. Why we have chosen the right hand bearing here? If we look into the loads on pinion, for the same torque it will be more than the loads on the gear, first stage gears, because the size is bigger. So, reaction loads, that is vertical and horizontal loads, will be less on right hand side bearing, and if we lock the arrangement what we have done in that way, right hand side bearing will take the axial load, and finally, we will see that for same size of bearing or even if different, life will be more or less same for both the bearing. That is a good designer's choice. In this case, it is on right bearing which is with less radial load, which I have discussed now. You can see this axial load is acting in this direction, and this is in by amount it is 673.35, that is FA3 minus FA2, which is 673.35 Newton. Next, we shall consider the bearing, are less expensive, but good enough for low range loads. So, in this case we are selecting a bearing, and we have considered escape bearing here. I would say that other bearing from other company carrying the same bearing number will have the more or less same load capacity, and life or other will be more or less same, because they are standardized and they are manufactured considering the same load condition and as well as the materials, heat treatment, finishing, etc., etc. Now, we have chosen a bearing SKF 6309. What does it mean? I have discussed up to the diameter 17 millimeter, the number is perhaps 6303. It will not match, but higher numbers 04 to higher numbers, it will be such that if you multiply with 5, then with the last 2 digit, it will give the internal diameter of the bearing D. In this case 09 into 5 is 45 millimeter. Now, what is 63? 63 is a series. Deep groove ball bearing series starts from 60, then 62, then 63, and there is 64. Higher this number, higher the load carrying capacity of same internal diameter ID, but outside diameter will be different depending on the series. And I would like to say that 6309 are widely used for gearboxes. 6.0 and 6.2 are normally not, and 6.4 also normally not taken. 6.3 are 6.3 series bearings are widely used. Now, let us see, this is from extract from the escape catalog, and what we find that for bearing number 6309, inner diameter ID is 45 millimeter, outer diameter is 100 millimeter, width is 25. It is matching what we took for the preliminary layout, and then corner radius 2.5 millimeter. This information is also important, because while we are finishing the corner, the steps of the shaft, so this dimension we should taken care of. At that corner, radius should be less than 2.5. We shall discuss this in details while we will make the detailed drawings or the assembly drawings. Now, next, with this bearing, there is the basic load carrying capacity is given. The dynamic load carrying capacity is 40130 Newton, whereas static load carrying capacity 29,200 Newton. We should keep in mind, by no means the radial load should be more than 29,200 Newton. It should be reasonably less than that. And from the dynamic load, we will calculate what might be the live. First of all, we will find out the equivalent load acting on the bearing. For that, we need two factors, which is for this bearings. In fact, it is for the almost all deep groove ball bearings. X is equal to 1 and y is 1.6. X factor is with the radial load and y factor is with the axial load acting on the bearing. Next, we shall find out the equivalent load on left bearing. Now, equivalent load P L is given by, sometimes it is written P also, P L. In that case, we have considered the left bearing, that is why we have given P L is equal to C 1. C 1, we should remember that C 1 is the factor depending on the load conditions, dynamic load conditions. Then X V F R and in subscript L means it is for left. X is the factor, already I have discussed. V is race rotating. In this case, for this gearbox, it will be 1, as the outer race is fixed, and Y is for axial load. Now, we have already calculated, we have already arranged this bearing in such a way, left bearing is not taking any axial load. So, directly F A L is put 0, and whereas the F R L, which we have already calculated, shown here, is 3591.5, and this C 1 factor has been taken as 1.5, considering medium shock load, which is mentioned in the problem on the estimated load on bearing based on nominal torque. Here, interestingly, I would like to say that in case of gear calculation, with the torque we have multiplied by 2. That is, from considering the shock load, one is medium shock load, and another point is that starting torque is always 200. The system is like that, starting torque is 200. So, for safe design of gears, we have considered a multiplication factor, or the we can say factor of safety also there. With the torque we have multiplied with 2. In this case, we have not multiplied with the forces any factor, because in the bearing calculation we are considering this factor in form of C1. However, with these values, what we find that on left hand bearing equivalent load is 5387.25 Newton. This is much less than the static load carrying capacity. So, apparently it looks very satisfactory, but now we have to calculate the life of the bearing. Now, life in hours is given by C by P to the power epsilon into 10 to the power 6 revolution, and C here is the dynamic load capacity, which is 40,130. So, substituting these values, we find we have directly calculated life in hours. So, life in revolution is first of all C by P, 40,130 divided by 5387.5 to the power, for ball bearing this value is 3. So, to the power 3 into 10 to the power 6 divided by the RPM 1500 RPM into the gear ratio. 1500 is the input RPM. So, divided by the gear ratio, first is gear ratio, which is 81 by 17, 1500 divided by the first is gear ratio, that is the RPM of the shaft, multiplied by 60, means we are considering this is in we have calculating in hours. So, we have divided this by 60. This value is quite high, 21,880 hours. It is more than double of required specified life. We are looking for a bearing life 10,000 hours, but what we have found, it is 21,880 hours. Now, let us see what can be done. First of all, we estimate the life of the other bearing, that means right hand bearing. In this case, the race rotation factor is 1 as well, the x is 1, and the radial load is there 2268.4, and the axial load is acting 673.35, which is multiplied by 1.6. 1.6 is quite high value, but in case of deep groove ball bearing, this is in higher side, whereas you will find in case of taper roller bearing and spherical roller bearing, this Y factor is less. So, we are getting the equivalent load on bearing is 5018.64 Newton, that is for right hand bearing, and the life estimated in the same way. The RPM is same for the shaft, load carrying capacity is also same, because we have taken the same bearing, it is 27,067 hours, which is also much higher, but these two values although not same, but close. Now, if we would make the locking arrangement in other directions, or the bearing locking is such that this can take load, the axial load is taken by both the bearing. In that case life would be different. Naturally, the life of right hand bearing would be more and life of left hand bearing would be less. However, with this arrangement we have somehow made not very close, but still more or less equal. So, it is justified that when there will be overhaul, both the bearings will be replaced by a new bearing, and it is somewhat towards the optimum life of the bearing. Although this is not a optimization, but somewhat. So, that I have explained why we have locked the right hand bearing and what is the results, but only thing is that both the lives are higher than the expected 10,000 hours. So, what we can do, we can look for such a bearing that which would be of less load carrying less dynamic load capacity, and we can verify what will be the life. So, what we have done in the same catalog, first of all, here it is not difficult to reduce the shaft size at the bearing. We have initially taken 45 millimeter at the bearing, where the bearings are sitting. Now, we can go for 40 millimeter easily, and for that in the same series we get a bearing 6308 series, that is for shaft 40, for which width is becoming 23 millimeter, but we shall keep the load center same. So, we can consider the same loading on the bearings, for which the dynamic load carrying capacity is 31,000 and static load carrying capacity is 21,400 Newton. Alternatively, we can go for the load carrying capacity dynamic load capacity and static load capacity keeping same as 6308, close to that we can go for 6211, a one series lower, but in that case shaft diameter is increasing 55 millimeter. It is not, it will not be a good design because the stepping, because the 55 will be very close to the root diameter of the pinion, which is integral with the shaft, but still it is possible we can go for that dimensions. Now, let us verify what will be the life. Here I have given that the root diameter of the pinion, second stand pinion is 55.39 millimeter, then a bearing of ID 55 may be selected. And if you look into the life in hours, what we find that C by P to the power epsilon into 10 to the power 6, only if we go for other bearings, then C is varying, P is remaining same because we are keeping the same load center, and in power there will be 3 because for ball bearings it is 3. Then we can compare in this way that C for 6309 divided by 6308 or 6211 to the power cube, which will give us how much reduction in the life, 2.17 and in other case 1.95 times. That means, if we go for 6308, then left hand bearing life will be 10,000, almost 10,000, because 21 21,880 hours divided by 2.17, it is slightly more than 10,000, and in case of right hand bearing it will be around 13,000 or so. With the bearing 6211, it will be divided by almost 2. So, in one case 10,500, 10,000 almost 11,000, in other case it will be around 14,000. So, these two bearings could be accepted, but looking into the shaft size, steps and more reliable operations, perhaps it is better to be with 6309, bearing 6309. And if we think in terms of cost, no doubt 6309 will be expensive than 6211 and 6308, but the difference is very small. So, probably being with 6309 will be better than selecting others. So, this is the end of step 5. Now, we shall consider the design verification of intermediate shafts. So, to verify the life of the bearings, what we should do is life of the shafts, or whether shaft stresses in the shafts are satisfactory, what we should do? First of all, in case of gearbox, the diameters of shaft is dominated by the size root diameter of the integral pinion and optimum bearing size mainly. This is particularly input and intermediate shafts. Output shafts we can go for other dimension, because that is also material is different, because that is not integral with the gears. The length is determined by the placement in gears, pinion, bearings, coupling, key size, seals, etc., and the optimum gap required between two consecutive elements. The shaft is automatically shaped during first layout and bearing selections. Now, here it is actually it should be therefore. Therefore, shaft is automatically shaped during first layout and bearing selection. So, now we shall look into the loads on the shafts. This is already we have determined, and then if we consider, again we shall calculate the bending moments in the shafts. We shall consider shear force diagram, bending moment diagram, all considering the in plane, vertical plane and horizontal plane, and then we will finalize the moment at sections. So, for vertical loads, what we find, we have simply written the reactions and then we calculate the shear force diagram. Now, looking into this and convention, I think the all of you are having the idea of calculating bending shear force diagram and bending moment diagram. In that case, shaft is bending in upward directions, therefore, we consider the shear force at the negative. So, first we have considered the 3518 at the left hand side, and then it is coming up to the next point, that is the middle of the pinion, and there we simply add 4533 Newton and we reach above the midline in the SF shear force diagram, and from that value 1014 Newton, again here at this point this value minus 2208, this value is added and we are coming down, and then we are reaching here. no sorry, from this point this is 1014.5 plus 1193.5, which is gives 2208 and shear force diagram. So, I expect that you are having the same idea about this shear force diagram. And similarly, for vertical plane we calculate also the shear force, sorry, we calculate the bending moment diagram. In the bending moment diagram, again as it is bending in the upward directions, we draw the bending moment in these directions, and these are the bending moment at these two sections. We have considered these two sections as there are bending moments are changing. Similarly, for the horizontal plane we estimate the, first of all we consider the shear force diagram, and next we consider the bending moment diagram in the same way. Now, in bending moment calculation in the horizontal plane, this is a horizontal plane, we should not forget about these two moments, which is due to the axial load at the pinion and the gears, and then final diagram is coming like this. Now, we have calculated bending moment and shear force diagram. We know what are the bending moments there, and now we will find the critical section and we will calculate the stresses there, which we shall consider in the next lecture, and we end our this lecture here. So, thank you.